Okay, so throughout this tutorial, I will use the example of Puchewe Cardón volcano, which is in Chile, which is known for its last eruption in 2011. If you want some more information, you can check those two papers, Bonadonna et al. And Pistolesi et al., which is going to give you an idea of the type, stratigraphy, chronology of the eruption. But what is important is, I mean, I'm not going to put too much emphasis on volcanological aspects. It's really more to give you an example, so don't pay too much attention to volcanological aspects in this case. So, Tephra 2 requires input parameters in meters, okay? By opposition to the typical geographic coordinate system, which is in latitude, longitude, and degrees, okay? The problem with that is that, for example, 1 degree in longitudes is not equal to the same distance in meter at different latitudes. Okay, so one thing that we can do is to go for UTM projected coordinates. So what this projected system does is that it projects a sphere onto very small tiles called UTM zones, which you see here, within which you can express distances in meter without distortion. Okay, so each of these UTM zone is defined by a number and a letter. The problem using these zones is that if you zone of interest spans over two zones laterally or crosses the equator, you're going to have problems of coordinates because they are not expressed as continuous from one zone to another. Okay, so this is typically the case, for example, for Cardon Cauge, which is here. I'm on Google Earth here, and you can see that this zone here is 18, this zone here is 19. So what I need to do is to find a way to make continuous coordinates in meters across those two zones, because UTM coordinates are typically expressed as easting and northing, so your x and your y. You need to be careful because in latitude longitude coordinates it's usually expressed as latitude longitude, so y and x, so that's something you want to be careful with. And what you see is, if you look at the coordinates, the easting, while I pass from a zone to another, you're going to see that it goes from 75,000 something to 240 something. Okay, so in TephraProb you can come here now and you can define, first we're going to start by doing a grid of points for calculation. Okay, so this is the interface that you have, and you can define your easting and northing as minimum and maximum values, and then it's going to ask you where, in which UTM zone you are and in which zone your vent is. Okay, so what you can do here is, for example, in our case of Cardon Cauge, it crosses, the grid is going to cross two UTM zones, right? So I want to click that here, in which case you have an option where you can define a west zone and an east zone. Similarly, if your grid crosses the equator, you can define a north and a south zone. And in the case it cross both, very annoying, you can define up to 4 zones of interest. Okay, in our case we're just going to define a west zone and an east zone. And going back to Google Earth, we know that from this eruption most of the ash went to Argentina. Okay, so we're going to define a zone that goes there. We're going to define a small zone because the larger your zone, the more time your computation will take. And similarly, the higher resolution, the more points you're going to have, and on more points a calculation is going to be performed, so it's going to take longer. In this case, let's define a zone that crosses around somewhere like that. Okay, so I defined my two zones. I say that my grid is going to cross UTM zones. So first I'm gonna define the minimum easting. Okay, so this easting is in the reference of my -18 zone. The minus means that we're in southern hemisphere. okay? But my maximum easting is going to be defined relative to my zone 19. Then we do the same for the northing, so my minimum northing and my maximum northing. Okay, and then we want also to say where the vent is, in which zone the vent is, in order to create the coordinates relative to the vent. In our case it's 18, and then we're going to set quite a coarse resolution because we don't want the calculation to take too much time, and we're going to give a name to the grid. Okay, and so now what we do is we can plot our grids. So here, if you have any kind of a firewall that tells you that MATLAB wants to connect to Google, you need to say yes, because the background here is Google Map. And so here you can see how our zone was defined. Okay, so that's one good thing. And now we need to click generate grids, which is going to create our grid. Okay, and then you can also reload a grid if you need to change some parameters. Let's just look at our grid folder now. Here. So that's the grid we just created, Cordon 2500, and we have various files in it. Most likely it's files you're never gonna see or use. It's just files that I use for plotting. So the grid in latitude, the grid in longitude, the grid in UTM easting, the grid in UTM northing, and what the calculation grid that's going to be used for Tephra2 is, well, I can choose, is this .utm files, which is just a 3-column file that gives you the easting, northing. And here I forgot to mention that in Tephra2 we just set the altitude to 0 due to the nature of the analytical solution of the advection diffusion equation. But then again, refer to the papers for more information on that. The second thing you will want to do is to create points of interests. And these points of interest can be used in two ways. Firstly, if you have run your probabilistic hazard assessment on grid, these points of interest would be used to extract what we call hazard curves. So you can define them on critical infrastructures, towns, or whatever you want. The second reason to do that is, as specified before, you can run TephraProb on your single CPU machine or on a cluster of computers. Depending on the size of the grid and the resolution, it can be very heavy to run it on a single CPU machine. So if you have trouble with that, what you can do is you can define these points of interest and run the hazard assessment only on these points of interest. And with that, in the end, you will not be able to draw maps like probability maps, but you will be able to at least calculate hazard curves on these points. So you go to inputs and points, and here there are again a few things to define. So first, let's call this set of point cordon POIs for points of interest. Okay. And then you just go on Google Earth and you look at points on which you want to define some critical aspects. So in this case, let's define that for these two locations. Okay. So first you click on your add points button, you enter then a name, latitude and longitude. So okay, let's add another point. So here in the names you should avoid special characters because these names are going to be used to save the files for the hascifs, and they might not like special characters. Okay, and last thing we need to define is again the vent zone. So in this case in -18 still, we don't add the letter, we just put a minus if it's in southern hemisphere and positive if it's in northern hemisphere. So now we can just plot to see if they fit where we want. Okay, so we should dezoom, but we can see that it's just good. Okay, so let's go and save this points. Okay, sorry, I was debugging, but the points were successfully saved.